First, we need to understand the idea of sampling variability. Sampling variability is just the fact that different samples give different results. Here's an example of sampling variability. If I randomly select two different samples of JFK students, and I calculate the mean height of each sample, the means of the two samples probably won't be exactly the same. After all, one sample might include a larger number of shorter students, and one sample might include a larger number of taller students. One sample might have a mean of 61 inches, and one sample might have a mean of 69 inches. Now that we understand the idea of sampling variability, we need to understand the idea of a sampling distribution. In statistics, a sampling distribution is a collection of possible outcomes based on all possible samples of a certain size. It takes a little bit of imagination to be able to understand the idea of a sampling distribution, so I'm going to challenge you to use your imagination. Imagine that I'm planning to do a study to estimate the mean height of the JFK student population. I don't have enough time to record the heights of all JFK students, so I'm planning to randomly select 50 JFK students to be my sample. After I select my sample of 50 students, I will record the height of each person in my sample, and then I will calculate the mean height of my sample. Hopefully, the mean height of my sample will give me a rough idea of what the mean height of the entire population equals. Since I decided to do a random drawing of 50 people, I know that I'm definitely going to get 50 people in my sample. However, I have no idea which 50 people are going to be in my sample. The specific group of 50 people that ends up in my sample depends on chance. There are many possible combinations of 50 students that could be selected, even though only one of them will actually be selected. Each possible sample of 50 students that I might select has its own sample mean. Also, because of sampling variability, the possible samples don't all have the same sample mean. The shorter samples have lower sample means, and the taller samples have higher sample means. Since the different possible samples have different sample means, I really have no idea what my sample mean will equal. There are probably some samples out there that would give me a mean height of 61 inches, some samples that would give me a mean height of 64 inches, and some samples that would give me a mean of 67 inches. If I was able to actually list out the means of all of the possible samples of 50 students that might be selected in my study, I would have a really long list of sample means. That collection of sample means would be my sampling distribution. You might want to imagine a gumball machine in which each gumball includes a different group of 50 people. When I randomly select my sample of 50 JFK students, one of those gumballs will fall down and become my actual sample of 50 students. Each gumball in the machine has a sample mean written on the front of it. Once my gumball of 50 people falls down, the number that's on my gumball is my sample mean. It's my outcome. If I was able to look at the number on each gumball in the machine, and then list out all of those numbers, that collection of numbers would be my sampling distribution. Basically, whenever a value is calculated with data from a random sample, the sampling distribution is just a collection of numbers that includes the value of the actual sample, along with the value of every other possible sample that might have been selected. At this point, you might be wondering, what if I wasn't calculating the mean of my sample? What if I was calculating some other value like the median of my sample or the standard deviation of my sample? Well, if I was calculating the median of my sample, then every possible sample that I might select would have its own median, and my sampling distribution would be the medians of all possible samples. If I was calculating the standard deviation of my sample, then every possible sample would have its own standard deviation, and my sampling distribution would be the standard deviations of all possible samples. Basically, whenever you calculate any type of value with data from a random sample, the sampling distribution includes the value of your actual sample along with the value of every other sample that could have been selected but was not actually selected. At this point, I wanted to mention that in statistics, it's important to understand the idea of a sampling distribution, but it's actually not necessary to be able to create sampling distributions. In this video, I will go through some exercises in which we create sampling distributions. However, I'll go through those exercises just because I think that they will help students understand the idea of a sampling distribution. I think that going through the steps of creating a sampling distribution makes the idea of a sampling distribution more concrete. Since it would be too difficult for us to create sampling distributions with data from large populations, we'll go through examples of creating sampling distributions with data from small populations. Also, I wanted to mention that in this video, we'll only focus on sampling distributions of means. We won't focus on sampling distributions of other types of values. We'll focus on means just to keep things simple for now.